Hello dear students, today I will discuss about second unit, that is calculus, second unit also calculus. First Rolle's theorem and Lagrange mean value theorem, or simply mean value theorem we can say. Okay, so just for Rolle's theorem and for mean value theorem, from the differential calculus, just we know about continuity of function, differentiability of function. Okay, just you have already studied what is continuity of a function, what is differentiability of a function in an interval. Just you have already studied in your previous class. So here, on the base of this continuity and differentiability, just we can get some results. That is just stated as a theorem, Rolle's theorem, mean values theorem. It's very very important theorem. Just we have study about what is the statement, how can we prove it, and its geometrical meaning, algebraic meaning, physical meaning of Rolle's theorem, mean values theorem. Okay, so just first take Rolle's theorem. Rolle's theorem statement, because this is a theorem, so there is a statement of this theorem, and just we will discuss in detail of this theorem, about this theorem. Okay, so statement, so very simple, very simple, both theorem. Okay, just remember the statement and what is the results interpreting from this theorem we can get, and use this for solving questions. Okay, so here a statement, if a function fx, we know about function, maybe polynomial function, maybe other type of function here also. If a function fx is, there are three conditions we will write like this for Rolle's theorem. First, continuous in closed interval AB. Suppose there is a closed interval AB. In this interval, function is continuous and differentiable in open interval. AB. And also, third condition is FA equals FB. Just this theorem also you have studied in your previous class, I think. Okay, if this means for this function, these three conditions are satisfied. If then we can get a point in this open interval. open interval. In this open interval means except a and b, just in between numbers, there exists at least one number. Then there exists at least one point or number, at least one point C. There exists at least one point C in A such that f dash c equals to 0. This is the statement of Rolle's theorem. So very simple statement. Just I think this you know about this statement because just in the previous class you have already studied it. Okay, a statement. What says we have a function. Suppose always we are denoting points, values of x, just like suppose in this x-axis. Okay, in this line, x-axis, just a, b are 2 points. Here a, here b. Okay, this is y. Y means what? Y equals to fx. The value of y is along this line. Value of x along this line. If this is interval, then in closed interval function is means just whenever we draw this function as a graphical curve, then what? Y equal to fx. So the curve may be like this. Clear? So here just statement says if this is function fx, means y equals to fx, for this function the value of y, that is fx, this is in between this interval, it is continuous. In open interval it is differentiable, and at these two corner points, that is fa and fb, both at the both point the value of function same. That is value of y same, fb. In this case, in between this there is a number c, means at which derivative of this function is equals to 0. So this is the statement of Rolle's theorem. Now, for proving it, we can prove it algebraically also by using definition of derivative, also geometrically by drawing diagram. Okay, so just these three conditions should be satisfied. These are the conditions for Rolle's theorem. If Rolle's theorem, condition for Rolle's theorem are satisfied for a function, then we can get a number, a point in between a and b such that derivative will be 0. Okay, this is the statement. Now, its proof is very simple. Just geometrically we can prove it very easily, and also algebraically you can prove it. Here suppose this is x-axis, this is y-axis, and origin. Now, point Suppose this is point A, x equals to A. That is here x equals to A. And here x equals to B. Just this value is what? X equals to B here. This is B. Okay. Now, just if we draw the function, graph of function, then here f equals to ab. That means the value of same value is here. This is x equal to A and x equal to B. So this is fa. This is fb. Both value are same. Third condition. And continuous. Curve is continuous. Function is continuous between A and B. Here x equals to B. Okay. So curve is continuous. So curve can be drawn just in between either this form maybe, or also maybe this form, or also maybe any type of curve maybe, but continuous, just like this maybe this type of curve, because these two values are same. And continuous curve, if curve is continuous, then at each point of the curve between A and B, tangent will exist, because curve is continuous. Just like this, if curve is continuous, then you can draw tangent here, 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 you can draw at all points tangent. So, if function, first condition, function is continuous between A and B, then curve is continuous from x equal to A to x equal to B. Just maybe like this, maybe any type of curve. Just increasing, decreasing, and increasing, decreasing both. And because curve is continuous, so at each point tangent will exist. Since f equals to fb, these two values are same. So, just we can see that here tangents you can draw like this, we can draw like this tangent, here can draw tangent like this, here can draw tangent like this, here can draw tangent like this. Just you can draw tangent at each point, but at this point, there exists some point, just like this. There exists some point at which tangent will be parallel to x-axis. Just this tangent, suppose this is point C1. This is point corresponding to C1, like this. This is C1, like this. This is C2, like this. Like this point, C3. Maybe one point, just maybe like this, na? Curve, or maybe like this, or maybe like this. So, maybe at least one point, maybe 2, 3, 4, 5, 6, 7 point. So, at C1, this is tangent. At C2, this is tangent. At C3, this is tangent. There is line parallel to x-axis. There are also another tangent, but these three tangents are parallel to x-axis. And we know the slope of the line parallel to x-axis is what? 0. Slope of the line parallel to x-axis is 0. We know. So, its slope is 0. And also we know that slope of the curve, slope of the tangent to the curve at a point is given by derivative of the function at that point. That means at this point, derivative of the function is 0. Y equals to fx curve. So proof, geometrically proof, we can see. Proof, if y equals to fx is continuous in AB, then just you can write if curve, just write like this. If curve y equals to fx is continuous in AB, then at each point on the curve between A and B, there exists tangent and since fa equals to fb, therefore there will be at least one point C belongs to AB, between AB, C, or you can write it like this, C between A and B, A and B, such that at that point slope of tangent at least one point C between A and B, such that at that point slope of tangent is will be 0, as tangent is parallel to x-axis. And also we know that slope of tangent to the curve at a point Here, say C. Slope of the tangent to the curve at a point is given by derivative of fx at that point. Therefore, f dash c equals to 0. Derivative at point c equals to 0. Hence, proved. This is by geometrical proof. The Rolle's theorem. Geometrical interpretation also you can say. Geometrical interpretation means what? Geometrical interpretation means here in between A and B there will exist at least one point at which derivative is equals to 0, that is at which tangent to the curve is parallel to the x-axis. At the point C, at that point slope of tangent will be 0 because as tangent is parallel to x-axis. Tangent is parallel to x-axis. Okay? Because there will exist some point where tangent is parallel to x-axis. And also we know that slope of tangent is given by the derivative. So at that point, so f dash c equals to 0. So this is the proof of Rolle's theorem. And we see that in the Rolle's theorem, the three conditions are satisfied, then there is a point C at which derivative is equals to 0. Okay. Now, just this is a geometrical interpretation also of Rolle's theorem and proof this also by using geometrical method. Okay. Now, algebraic interpretation, what we can say algebraically? Algebraically means suppose function is a polynomial. Okay, here we see that what? fa equals to fb. Here we see that what? fa equals to fb. Okay, so just algebraic interpretation of Rolle's theorem. Algebraic interpretation means if function here, just see if function, what function? If fx is polynomial function. This is algebraic interpretation. If polynomial function fx, then and its two roots are a and b. Two roots f, a and b. If fx polynomial function and its two roots a and b. If fx is polynomial and its roots a and b, that is what? Roots means what? Fa equals to 0 and also fb. Because ab are roots. This is polynomial function and we know that every polynomial function is continuous. Every polynomial function is also differentiable. So three conditions are satisfied. If fx is polynomial function and its two roots are a and b, that is fa fb is equals to 0. Fa fb equals to 0, but that is both are equal. So these three conditions, three conditions of Rolle's theorem are satisfied. If three conditions of Rolle's theorem are satisfied, then there exists at least one point. There exists at least one point between A and B. Between A and B. At least one point between A and B. At least one point C. Between A and B such that f dash c equals to 0. That means what? F dash c equal to 0 means, because this is polynomial function, fx is polynomial function, then its derivative is also a polynomial function. If its derivative is also a polynomial function, then its root is what? F dash. If this is a polynomial function, if c is its root, then f dash c equals to what? 0. That means what? Implies c is a root of f dash x. This is algebraic interpretation. If fx polynomial and its roots are a and b, then between a and b there exists another root. Not another root, there exists a point c which will be the root of the f dash x equals to f dash x. Okay. So at least one root. That means here at least one point. So at least one root of f dash x exists in A. So what is algebraic interpretation? If fx polynomial, its two roots a and b, then there exists at least one root of fx exists between a and b. Okay, this is algebraic interpretation. Now, questions related to this theorem. Just finding the value of c or verifying the Rolle's theorem. Just verifying Rolle's theorem means what? Just first of all, just discuss about the satisfaction of three conditions for a function in interval, and then find the value of x by taking f dash x equals to 0, and one of the value must lie between a and b, that interval point. Okay. Finding the value of c must lie between the endpoints, means a and b, between a and b. That is, then Rolle's theorem will satisfied. So for verification of Rolle's theorem, just we have to first discuss about satisfaction of Rolle's theorem, means continuity, differentiability, and fa equals to fb. Okay, so take questions. Verify Rolle's theorem for function sin x by e to the power x in 0 pi. So take these questions. Solution. Given function is what? Given function is fx equals to sin x upon e to the power x in 0 pi, in interval 0 Okay. So just you see the function whether, because for verification of Rolle's theorem, just we have to discuss about 3 points. Function is continuous in closed interval. Here in 0 pi interval is 0 pi, but for Rolle's theorem, this function must be continuous in the closed interval, differentiable in the open interval, and f equals to fb. Okay, so here just we see that here we see that sin x and e to the power x both are continuous function, and e to the power x is not equals to 0 any times. So continuous function upon continuous, and also this is differentiable function, this is differentiable function. Differentiable function upon differentiable function is also differentiable. Here we see that sin x and e to the power x both are continuous and differentiable function. Just you have to give the logic. Differentiable function. So first and second condition of Rolle's theorem satisfied are satisfied, and also f of 0 equals to sin 0 upon e to the power 0 equals to 0, and f of pi equals to sin pi upon e to the power pi equals to also 0. Because sin pi 0 and sin 0 0, so both are 0. That is implies f0 equals to f pi. Implies third condition is also satisfied. Thus, all conditions of Rolle's theorem are satisfied for given function. Okay. Now, for verification of Rolle's theorem, just we have to find the value of c. That is by taking f dash c equals to 0. Okay. According to Rolle's theorem, f dash c equals to 0 for some c belongs to 0 pi. That is, we have to find the value of c. That is, now we have to find the value of c, which we must satisfy, which will be in the open interval 0 pi, which will be in the open interval 0 pi. Then Rolle's theorem will be verified. This is our process. Okay, how can we verify Rolle's theorem? Just we have to find the value of c. First of all, just discuss about three conditions are satisfied by given function in the interval. And now according to Rolle's theorem, this is equal to 0 for some c belongs to 0 pi. That is, we have to find c, and that c must be lie in the interval 0 pi, and then Rolle's theorem will be satisfied. So now just find f dash c, means first of all find derivative. Okay, we see that derivative f dash x, just differentiate it, numerator upon denominator. So what? Denominator square, denominator into differentiation of numerator sin x cos x minus sin x into e to the power x. This is derivative. Okay, this is derivative, and this implies f dash c, f dash c is equals to 0 now. F dash c equal to 0 implies f dash c equal to 0, this is equal to 0, e to the power c cos c minus sin c e to the power c upon e to the power 2c equals to 0. Now we can solve it. This is multiplied to 0. Now e to the power c cos c minus sin c is equals to 0. Just e to the power c is not equals to 0. You know, exponential function, value of exponential function is not equals to 0. So cos c minus sin c equals to 0. That is cos c equal to sin c, that is tan c. We can write tan c equals to 0. Sorry, 1. How can you write like this? Cos c equals to sin c. So sin c by cos c equals to tan c equals to 1. So tan of c equals to 1 means what? This means c equals to pi by 4. Tan c equals to 1, tan pi by 4 equals to 1. So pi by 4, that is belongs to, we see, which belongs to, we see that pi by 4 is lies between 0 to pi. Pi by 4 lies between 0 to pi. implies that is pi by 4 belongs to 0 pi. C equals to pi by 4 implies the Rolle's theorem verified. Main thing is what? Value C. Just differentiate function and equals to 0 and find a value, and that value must lie between interval. That is the value of C. Must lie in the open interval. Here, value of C lie in the open interval, so Rolle's theorem is verified. Okay, so this is the process for verifying Rolle's theorem for a given function in a given interval. Okay, now take a second question. Just for root, about root, because we know that if fx is polynomial function and its two roots, just take a question. Second question. Show that the function, equation x cube minus 3x plus c equals to 0, where c is a real constant and cannot have two roots in the open interval 0, 1. Okay, so this is question because it is given as a root, related to root. So for this type of solving this type of questions, we can use algebraic interpretation of the Rolle's theorem. See a given equation is, here given equation is what? Fx equals to x cube minus 3x plus c. X cube minus 3x plus c equals to 0, where c is a real constant. Okay, where c is a real constant. Where c is a real constant. Just write like this. This is equation is given. This equation is given. This is equation. This is equation. Just we write like this. Polynomial fx equals to x cube minus 3x plus c equals to 0. Just we can write fx equals to 0. Where fx is polynomial. Fx is polynomial. Let fx equals to, fx is a polynomial. Okay. Now, according to algebraic interpretation of Rolle's theorem, we know that if fx is a polynomial function and this is equation and its roots are a and b, that is fa and fb is equals to 0, that is ab. If this and this is polynomial, then there exists, this means there exists, c belongs to ab, there is c, there exists a root of f dash x. There is root of f dash x. That means just solve f dash x is equals to 0. F dash x is a polynomial. This is a polynomial. This is the equation. And solve this equation. Just find the value of x. If one of the value of this x lie in the interval ab, in the interval AB. Then we can say that this having two roots. If any value of this does not lie in the interval AB, that means fx cannot have more than two roots. Because two roots means fa equals to fb equals to 0. Two roots means if two roots having, then satisfying Rolle's Theorem's conditions. And in that case, derivative f dash x equals to 0 having a root between a and b. But here we see that its root does not lie, any of its root does not lie in the interval AB. That means fx cannot have two roots, because this is converse is used. Okay? Because if it have two roots, then there must exist one root of this between a and b. So for that, in these questions we have to show that what the given equation cannot have two roots in the open interval. Okay, cannot have two roots in the open interval. We have to show that given equation cannot have two roots in the interval 0, 1. According to questions, just we have to show that this equation cannot have two roots in the interval 0, 1. So for having two roots, just we can use algebraic interpretation of Rolle's theorem. For that, just you have to find the value of x by taking f dash x equals to 0. And if any of the value lie in this interval, then you can say that can have roots. If not, then cannot have. Okay? So here we have fx equals to what? X cube minus 3x plus c implies its derivative. Just find derivative. Derivative equals to 3x square minus 3 this. So f dash x is equals to 0 implies 3x square minus 3 equals to 0. So here x square is equals to 1. X equals to plus 1 minus 1. Plus minus 1. And we see that any of these are not lying in the interval 0, 1. So just we can write that now you can write here just implies that the value of x for f dash x is equals to 0, that which implies that any value which implies that any value of x for which for f dash x equal to 0 are not lie in the interval 0 1, which implies that any value of x for f dash x equal to 0 are not lie in the interval 0 1, because minus 1 is not in this interval, plus 1 is also not in this interval because this is open interval. So for f dash x equal to 0, any value of x for f dash x equal to 0 are not lie in the interval 0 1. That means, so by algebraic interpretation of Rolle's theorem, so by algebraic interpretation of Rolle's theorem, f dash fx equal to 0, that is given equation x cube minus 3x plus c is equals to 0 cannot have two roots in 0 1. Clear? So by algebraic interpretation of Rolle's theorem, we know that if fx having two roots, then f dash x equals to 0 must have a root in the interval 0 1. But here any value of x for f dash x equal to 0 are not lie in the interval 0 1. So by algebraic interpretation of Rolle's theorem, given equation, that is fx equal to 0, is this cannot have two roots in 0 1. Okay, so algebraic interpretation can also be used for taking decision about a polynomial equation, that is polynomial equation, that is for polynomial function, for the polynomial function, by making, because left hand side just take fx equal to this is the polynomial function, and then just use algebraic interpretation. So this is also important. Okay, now take third question. Just for solving this type of questions, we have to find derivative fx, and just taking derivative equals to 0, solve it. If any of the value lie in the interval, then we can say equation can have two roots. But if any value does not lie in the interval, then cannot have two roots. Okay, so this is the use of algebraic interpretation of Rolle's theorem. Now third question, just take another question. For verification of Rolle's theorem, just you have to find derivative equals to taking derivative equals to 0 and finding the value of c, and c must lie in the open interval for the given interval, and condition are satisfied, just discussing, and then you can verify it if c lie within the interval. If not lie, then Rolle theorem is not applicable. For applicability of Rolle theorem, here just discuss the applicability of Rolle's theorem in the interval -1 1 to the function fx equal to mod x. This here given function. Given function is fx equals to mod x. We have to check the applicability. We have to check the applicability of Rolle's theorem. Rolle's theorem for this function in the interval -1 to 1. This closed interval. Just we know the Rolle's theorem. For the Rolle's theorem, what function should be continuous in this interval? Function should be differentiable in this -1 and 1 interval, and fa equals to fb. Here, out of 3 conditions, 2 conditions are satisfied and 1 condition is not satisfied. We see that here, we see that only 2 conditions of Rolle's theorem are satisfied, as continuity on -1 1 and f -1 equals to f plus 1 equals to 1, because mod 1 equals to 1, mod -1 equals to 1, so both are 1. Okay, but second condition, that is differentiability of fx in -1 1 is not satisfied, because mod x is not differentiable at 0 belongs to -1 1. Okay. Clear? So because 0 lies between -1 to 1, there is a point at which function is not differentiable. So second condition differentiable, first condition continuity, second condition differentiable, third condition f equals to fb. So first and third condition are satisfied. And second condition is only 2, first and third. Okay. Satisfied, first and third satisfied, second condition not satisfied. Thus, the Rolle's theorem is not applicable to the function fx equals to mod x in. So this is solution of this question. Okay. So just we see that what is Rolle's theorem, what is the statement of Rolle's theorem, what is the interpretation of geometrical interpretation, proof of Rolle's theorem, geometrical interpretation, algebraic interpretation. Algebraic interpretation means about root of, and geometrical interpretation means just find the value of c which must lie in the interval. Then Rolle's theorem can be applied. Rolle's theorem will applied and can be verified. If c lies between a and b, then Rolle's theorem is verified. And this is for checking whether applicable or not. For applicability, three conditions must be satisfied. If one of the condition is not satisfied, then Rolle's theorem is not applicable. If all the conditions are satisfied, then Rolle's theorem can be applicable. For that, just check whether derivative f dash c equals to 0 implies the value of any, at least one value of c lie in the interval. Then Rolle's theorem will be verified. Okay, so this type of questions are frequently asked in the question exam. So just to do some questions, there are many questions in different type of books. Just solve for finding c and whether c lies between the interval. Then we can say to verify. Means questions related to verification of Rolle's theorem. Just you have to practice. Okay. Also, algebraic interpretation is important. Now, mean value theorem. Mean value theorem. Just first, we will state Lagrange's mean value theorem, and then Cauchy's mean value theorem. Actually, mean value theorem is main theorem is Lagrange's mean value theorem, and Cauchy's mean value theorem is generalized form. This Lagrange's mean value theorem is particular form of Cauchy's mean value theorem. Okay, so here just mean value theorem Lagrange's mean value theorem. Mean value theorem. Lagrange's mean value theorem is state mean, because just like Rolle's theorem, Lagrange's mean value theorem having a statement, and also we have to prove it. Very simple. Just you know about it's a statement from your previous class also. So here just we have to state Lagrange's mean value theorem statement. Okay. So just similar to Rolle's theorem, here only two conditions are required. If the function fx only two conditions are there. Okay. First is if the function fx is continuous in closed interval AB and differentiable in open interval. In open interval AB. Same as Rolle's theorem, two condition. Third condition is not required here, f equal to fb, that is for Rolle's theorem. Here the statement in this there. There exists at least one point C in AB such that f b minus fa upon b minus a equals to f dash c. This is a statement. Okay, in the Rolle's theorem there is a condition f equals to fb and then f dash c equals to 0. Here f equals to fb, that f dash equals to 0. So Rolle's theorem is a particular form of Lagrange's mean value theorem. Lagrange's mean value theorem is a particular form of Cauchy's mean value theorem. Okay, so here just Lagrange's mean value theorem, this is the main statement. Okay, so this statement is useful for solving questions and it's a geometrical meaning also. Okay, it can be proved very simply. Just you know about its statement and just you already find out the value of C which lies in AB for verification of Lagrange's mean value theorem. So here by using this statement just we can solve some questions. Now proof of this. Its proof can be done by also geometrical form and also algebraic form. Okay, so algebraic form, just up to this stage we know about Rolle's theorem. If three conditions are satisfied for a function in an interval, then there is a point, at least one point C in the open interval, such that at that point derivative is equals to 0. So here, just for proving this, here function fx satisfying these two conditions, then we can get at least one point C like this. So to prove it, we can suppose to prove Lagrange's mean value theorem. Lagrange's mean value theorem. Let us consider the function fx equals to fx plus a into x, where a is a constant such that fa equals to fb. Just let us consider the function fx equals to fx plus ax in combination is denoted by fx, where a is constant such that f equals to ab. You suppose that fx is a new function such that f equals to fb. Then fa, we get fa means fa plus a into a. This is fa plus a into a equals to fb plus a into b. Just we consider this function such that f equals to fb. From f equals to fb we get here, from here, just fa means a and b means x equal to b. So from here we see that fa minus fb is equals to transfer to right hand side a into b minus a. From here just we see the value of capital A. So value of capital A equals to minus f b minus fa upon b minus a. Just we can write like this. Here fa minus fb, so minus common, fb minus fa. Minus common, fb minus fa upon b minus a equals to. This is the value of a, first equation. Okay. Just for proving this theorem, let us consider the function this, where a constant, such that this, from this condition we get a equals to this. Now since here fx is continuous in AB and x is always continuous therefore fx plus a into x is also this is equals to what? Or fx is also continuous in AB. Also, since fx is differentiable in AB, therefore fx, that is what? Fx plus a into x. Therefore fx equals f dash x equals to f dash x. This exists. That is fx is differentiable in AB. Differential in AB. That is our capital Fx, this. Capital Fx, this. satisfies all the three conditions of Rolle's theorem. F equals to Fb, third condition, Fx is differentiable in AB, second condition, Fx is continuous in AB, first condition. Here we see that Fx satisfies all three conditions of Rolle's theorem. Okay, just we see that Fx satisfies all three conditions of Rolle's theorem. Therefore, by using Rolle's theorem, this symbol is used for there exist. There exist, or just write it. There exists a point C in AB such that f dash C is equals to 0. F dash C equals to 0. Implies f dash C equals to 0, implies f dash x, here C, so f dash C plus A equals to 0, so implies A equals to minus f dash C. According to Rolle theorem, just we can get capital constant is equals to minus f dash C. Now this is second equation. Now from equation 1 and from equation 2 we get, from equation 1 and 2 we get from equation 1 and 2, we get what? A equal to 12, minus cancel, f dash C equals to this. So FB minus FA upon B minus A equals to f dash C. So this is hence proved. FB minus FA upon B minus A equals to f dash C. This is the condition of Lagrange's mean value theorem. So by constructing a function fx equal to this, we can prove by using the condition of Lagrange mean value theorem, we can get this result. So very simple, proving Lagrange's mean value theorem. This is important also as a question. Okay, so state and prove. Okay, this is the proof. Just using differential calculus, we proved it. Okay, now see its geometrical interpretation. Okay, Lagrange's mean value theorem geometrical interpretation is first form. This is, and another form can also be written by of Lagrange's mean value theorem, because that is main thing for defining or for stating Taylor's theorem. So just that is another form of the Lagrange's mean value theorem. Okay. Now, just we see what is the geometrical interpretation of Lagrange's mean value theorem. Geometrical interpretation. Geometrical interpretation. Just suppose this is y-axis, this is x-axis, this is origin. Clear? Now, condition is what? Continuous from A to B. This is x equals to A. This is x equals to B. Okay. So suppose here it is not required of f equals to fb. So we can suppose this is f, and also here just suppose this is fb. This is f a. We can suppose at x equal to a, this value is what? A, and this value is what? B. And function may be any type. So function may be like this, a function may be like this, function may be like this. Just continuous function from this point to this point. Okay, so here just suppose like this. This is point A, this is B. Curve AB. What is this? This is fx. Y equals to fx. Curve. Now we can draw just joining these two. Chord AB. And since curve is continuous from A to B, between A and B, so at each point there are tangents. Here is tangent also, but tangent at this point, there is a point here, just tangent is because tangent is at each point tangent exists because curve is continuous. So here is a tangent, here is a tangent, here is a tangent, but this tangent, there is a point where tangent is parallel to chord AB. Okay. So here C. This is the point C. So x equals to C. Just between A and B, there is a point. At this point, this is tangent. Okay. Suppose this is L. This is L. This LM is tangent. At this point, and this tangent is parallel to this. The slope of this tangent is equal to the slope of this chord. Slope of tangent LM is equals to slope of chord AB. Okay, so here LM is parallel to AB. So slope of tangent LM is equals to this, and according to the differential geometry, slope of this tangent at this point x equals to c, is given by the derivative of curve at this point. So that is f dash c, and slope of chord AB, its coordinate is what? FB and at B, and its coordinate is what? A, F. So this slope of a line segment joining two points, y2 minus y1 upon x2 minus x1, FB minus FA upon B minus A. This is condition of Lagrange's mean value theorem. Okay, and this condition, both are equal. That is geometric mean value theorem says what? If function fx is continuous from x equal to a to x equal to b, then at each point of the curve having some tangents, and there will be a point at which tangent is parallel to the chord joining the points a fa and a b and b, joining the curve from a to b. So joining the point a and b, end point of the curve. So this is the geometrical meaning. You can say geometrical meaning how? Just if a curve has a tangent, at each point, because continuous it is what? If a curve has a tangent at each point means what? Curve is continuous from A to B, curve AB. Then there exists a point on the curve. At which the tangent to the curve is parallel to the chord joining the endpoints of the curve. So this is the geometrical interpretation. Okay. Tangent is parallel to the chord. There is a point where tangent is parallel to the chord AB. AB is the endpoints of the curve. So this is geometrical meaning. Okay. That is, if a curve AB has a tangents at each of its points, means if function is continuous from A to B, then curve having tangents at each point. That is, if a curve AB has tangent at each of its points, then there exists a point C on or L. You can see here L. There exists a point L on the curve such that at which the tangent is parallel to tangent is parallel to the chord AB. This is geometrical meaning, geometrical interpretation of Lagrange's mean value theorem. Okay. Here also curve may be in this type, just like this. Also you can draw like this curve. So here tangent, here tangent, here tangent, here tangent, here tangent. Just we can draw parallel tangents at many of the points, but at least one point is there. Okay. So this is the geometrical meaning of Lagrange's mean value theorem. Okay, it's another form. Just we see, it's another form. There is a point, so just now we can state it in other way, just like this. There exists a number lies between 0 to 1. Then we can also state Lagrange's mean value theorem as, suppose here interval. Just we take interval, how? Interval is just like AB. AB is interval. Just suppose first value is A and interval length we know. B is equals to A plus H. Okay? That is what? B equals to A plus H. That is B minus A equals to H. H is the interval length. Length of the interval. H interval. If we use this, then a statement, what will be the statement? Since C lies between A to B, means C belongs to A to B, and C can be written, C lies between A to B, greater than A and less than B. That means C can be written as A plus some value, because its length is H. So at most its value may be A plus H. Open interval. So B equals to A plus H. So just less than A plus H. That is A plus H theta H, where theta lies between 0 to 1. If we take a number, just real number, lies between 0 to 1, then if we use theta H, that means theta H is what? A number less than H. So, as theta vary, A will go to the up to B. So C can be written as C equal to A plus theta H, or theta lies between 0 to 1. So in place of theta, just we can write A plus theta H and say that theta lies between 0 to 1. So condition F B minus FA upon B minus A is equals to F dash C. It can be written how? FB. FB means F A plus H minus FA upon B minus A. B minus A equal to H. H equals to F dash C means A plus theta H. This is a new format. This is a new format. From here we can write like this: F A plus H, H transfer to here, F A plus H, F dash A plus theta H, and theta lies between 0 to 1. So we can write Lagrange's mean value theorem in this form. So another statement: if function a statement if function fx is first continuous in A plus H, and second differentiable in A plus H. Just in place of B, just write A plus H. Then we can write, then there exists a number theta lies between 0 to 1 such that f a plus h equals to f a plus h f dash a plus theta h. This is another form of Lagrange's mean value theorem. Second form. Okay, second form. Second form, Lagrange mean value theorem. Second form of Lagrange mean value theorem. If function is continuous in this interval, differentiable in open interval, then there exists number theta. Theta lies in 0 to 1 such that we can write like this. This is the second statement, very very important, because just by using this form of Lagrange mean value theorem, just proceed in the same way as taking this is another function. Then we can get generalized mean value theorem, that is called Taylor's theorem. Just I will discuss in detail in the next class about Taylor's theorems with reminders form also. Okay, Taylor series, Maclaurin series. So this is second form of Lagrange's mean value theorem. Okay. Now we will solve some questions from this. Take question 1. State the theorem. If the mean value theorem is taken as just fb minus fa equals to b minus a f dash c in this format, they determine the value of c lying between a and b. Okay. So here, first of all, state the mean value theorem. Just give the statement. Okay. So here, the given function is what? Solution. Mean value theorem is Lagrange's mean value theorem. Just we have to verify. Here, the first of all, give a statement. Just we know if fx is continuous in closed interval and differentiable in open interval. Just we know this is the definition. This is the condition of Lagrange mean value theorem. Then there exists a point C in AB such that FB minus FA upon B minus A equals to F dash C. This is the mean value theorem. Lagrange mean value theorem statement. Okay. If these two conditions are satisfied and there exists a point C in AB such that this. Okay, here given function is fx equals to, what is given? Fx equals to x minus 1, x minus 2, x minus 3, a0, b4, x minus 1, x minus 2, x minus 3. This is given function and interval, and also a equals to, interval a equals to 0 and b equals to 4. This is the point f, a equal to 0, b equal to 0. Just we have to find the value of c lying between a and b. Okay, a and b means 0 and 4. Here, just see that after multiplying it, we can get a polynomial. Okay, just if we multiply this, so we can get a third degree polynomial. So every polynomial function is continuous, and after differentiation of this third degree polynomial, we can get another second degree polynomial that is also differentiable, because polynomial function is differentiable. So fx is continuous and differentiable in the interval ab, that is 0, 4. And while taking this condition, okay, just we have to find first of all what? Derivative. So here we see that differentiate with respect to x. Differentiate with respect to x, we get the derivative f dash x is equals to just product of three function. That means we can write like this: x minus 1 into x minus 2, derivative of this 1, plus x minus 1 into x minus 3, derivative of this, plus x minus 1 into 2 into x minus 3. The product of three function. So derivative of this, and then derivative of this, and then derivative of this. This can be solved: x square minus x minus 2x minus 3x plus 2 plus x square minus x minus 3x minus 4x plus 3, x square minus 2x minus 3x minus 5x plus 6. So it can be solved: 3x square minus 3 for 7 minus 12 minus 12x and 2, 3, 5, 6, 11 plus 11. So this is f dash x. This is f dash x. Okay. So what? Now this is derivative. Okay. Also, just we have to find the value of c by using this condition. Lagrange mean value theorem gives this statement here, because Lagrange mean value theorem can be used for this given function here. So because this is continuous, also differentiable, so we can use Lagrange mean value theorem for that. Here f a f b, here f a means what? f0, f a f0, f0 means here 0, just putting 0, then minus 6, and f b, that is f4, they have 4 minus 1, 3, 4 minus 2, 2, 1, 1 to 3 means 6 plus 6. So both values are minus 6 and plus 6. Now just we have to find the value of c. So just put the value f a, f b, and a and b here in left hand side. Here f dash x equals to this, so f dash c means this. So c. Now by mean value theorem, fb minus fa upon b minus a equals to f dash c. Just use all the values a0, b4 and fa minus 6, fb plus 6. fb plus 6 and fa minus 6 upon b4 minus 0 is equals to f dash c. F dash c you can find f dash c. F dash x equal to c. So 3c square minus 12c plus 11. 3c square minus 12c plus 11. So just solve it. Okay. 6, 6, 12. 12 by 4. 3. 3 equals to 3c square minus 12c plus 11. So from here we see that 3c square minus 12c minus plus 8 equals to 0. So this is our equation for finding the value of c. And on up here we can get two value of c. So just solve it. Quadratic equation minus b plus minus root b square minus 4ac by 2a. So minus b means 12 plus minus root b square. Root b square means minus 12 minus 12 square means 1 4 4 minus b square minus 4ac. 4 into a into c. 4 into 3 into 8. 96. Okay, upon 2 into a, 2 into 3. So after solving this, just 144 minus 96, 48. So here we see that 12 plus minus root of 48 upon 6, c equals to. So we can write c equals to, two values are there. Here 48 can be written as 3 into 16, 48. So 4 and 3, root 3, 4 root 3. 4 can be 4, 12 plus minus 4 root 3 upon 6 divided by 2. So we can get what? C equals to just 2 plus 2 by root 3. 2 plus 2 by root 3. 2 plus 2 by root 3 here. Just 2. Here 3. Here 3. Here 2. 3. 3 root 3 by 3 root 3. 2 by root 3. So 2 plus root 3. 2 by root 3 and plus minus 2 by root 3. So 2 plus 2 by root 3 is 2 by root 3. 2 plus root 3 gives 3 point something. And 2 minus gives 1 point something. That is, both values lies between A and B. So finally, we see that C equals to 2 plus minus 2 by root 3 belongs to 0, 4. Okay, both value. 2 plus minus 2 by root 3 lies between, that is, both values of C. 2 plus 2 by root 3 and 2 minus 2 by root 3 lies between 0 and 4. So this is our answer, the value of C. So just for a given function, just you check whether these two conditions are satisfied, then we can use Lagrange mean value theorem, this formula, and we can find the value of C, that is in between value A and B. Just find derivative, find values and use this relation. We can get the value of C. Just see whether C belongs to the interval or not. Okay. So this is questions related to. Now take another question. By mean value theorem, we can solve different type of questions here. Just take next question. That is what? Prove that if this is our mean value theorem. In these questions, just we have to prove. Okay. We have to prove that b minus a upon 1 plus b square is less than tan inverse b minus tan inverse a is less than b minus a upon 1 plus a square. Just we have to prove this. Okay? Where 0 less than a less than b less than 1. This. A less than b less than 1. 0 is less than this or this. Okay, and also we have to show that second part. Also, we have to show that I by 4 plus 3 by 25 is less than tan inverse 4 by 3. Tan inverse 4 by 3 is less than 5 by 4 1 by 6. It can be proved by using this result very simply. Okay, just putting some value for a and b, then you can get this. So first of all, we have to show that this, where a like this, 0 and this. Okay, so by mean value theorems, we can see that we have to prove that this. Just for proving it, think about it. How can we get this? What will be the function for that? Okay. How can we get this? We can suppose that this is FB, this is FA. Same type of thing. So, we can suppose to prove it, let suppose function fx equals to tan inverse x. Then fb minus fa, tan inverse b minus tan inverse a. So just we can start from here. Clear? Now, just differentiate it. What? 1 upon 1 plus x square. Tan inverse 6 as a series continuous function because polynomial function, just like so. Differentiable also. So by using mean value theorem. By using mean value theorem. By using mean value theorem. Because this is continuous and differentiable also. So we can use mean value theorem for this function. Okay. Theorem. Here A and B, A less than B. AB may be the interval. So in this interval, by using mean value theorem in AB, we get what? FB minus FA upon B minus A equals to F dash C, where A less than C less than B. Clear? So this implies what? Tan inverse B minus tan inverse A upon B minus A is equals to 1 upon 1 plus C square. F dash x 1 upon 1 plus x. So f dash 1 upon 1 plus C square. Now just see that here this is equation first. Clear? Tan inverse B minus tan inverse A upon B minus A equals to 1 upon 1 plus C square. This is mean value theorem. Gives this result. Now, just we require this type of relation. So for that, since here A less than C less than B and all are positive values, that's why we can write like this. Now, since 0 less than A less than C less than B less than 1, because C lies between A and B. A greater than 0, B less than 1. Okay, just B also less than 1 here given. B less than 1. B less than 1. It means just we can write A less than C less than B implies A square less than C square less than B square. Implies 1 plus A square less than 1 plus C square less than 1 plus B square. Clear? Now, we require 1 upon 1 plus C square. So just invert this. Then inequality will be changed. After this line, just we can write, or just here, suppose just no, after this line just we write here 1 plus A square is less than 1 plus C square is less than 1 plus B square. Invert this, 1 upon 1 plus A square is greater than 1 upon 1 plus C square is greater than 1 upon 1 plus B square. Just invert this, then inequality will be changed. Less than to greater than. Now just write like this. 1 plus B square is less than 1 upon 1 plus C square is less than 1 upon 1 plus A square. Okay? Now, B is greater than A. That is just we can multiply here b minus a, positive quantity everywhere. So just we can write b minus a upon 1 plus b square less than b minus a upon 1 plus c square just less than b minus a upon 1 plus a square. Just multiply b minus a in everywhere. Okay. Now this is equation 2. This is equation first. This is equation 2. Now using this 2 we can get this result. Just put 1 upon 1 plus c square is equals to this here. Just see here. After this line here, right? Using 1 and 2 we get. Equation 1 is this, equation 2 is this. Just here 1 upon 1 plus c square, 1 upon 1 plus c square. So 1 upon c square is equals to, this is equals to this. Also we can write it as tan inverse b minus tan inverse a equals to b minus a upon 1 plus c square. This is equation 1, suppose. This is equation 1. Then equation 1 and 2, using equation 1 and 2, b minus a by 1 plus c square. This can be used here. We get b minus a upon 1 plus a square is less than, in place of this, just you use this here, tan inverse b. So we get tan inverse b minus tan inverse a is less than b minus a upon 1 upon this. Hence proved. First part is proved. Okay. So just here we use mean value theorem and also this condition for getting this type of relation. Okay. Now second part is what? Just we have to show that this is right. So for getting this, here we see that only we have to prove, put what? Tan inverse 4 by 3. Just if b equal to tan inverse 4 by 3, and for solving it, just take a equal to 1, because a if we put a equals to what? 1 and b equals to, if we put a equals to 1 and b equals to 4 by 3, b equals to 4 by 3, then clear? Use here a equals to 1, b equals to 4 by 3. B equals to 4 by 3 because we require tan inverse b by 4 by 3. So tan inverse 4 by 3 means here just we can suppose b equals to. Then if we put in above result, then here a equals to, b equals to 4 by 3 minus 1 upon 1 plus 1 square a square is less than tan inverse b equals to 4 by 3 minus tan inverse 1 less than b 4 by 3 minus 1 upon 1 plus 1 square. Just see what here 4 by 3, 3, 3, 1 by 3, 1 by 3, 1 by 6, 1 here 2, 1 by 6 is less than tan inverse 4 by 3 minus tan inverse 1 means 5 by 4 less than 1 by 6. Okay, just add on both sides. sorry, here b square is there. Here b square. Here b square. B square means 4 by 3 square. So here we get what? 16 by 9, 9, 16, 25, 25 by 9, 1 by 3, 1 by 3, 1 by 3, 3, 25, 3 by 25. This 3 by 25. Now transfer or just add pi by 3 in 3 places. So you see that pi by 3, pi by 4, pi by 4 plus 3 by 25 is less than 10 inverse 4 by 3. 4 by 3 is less than pi by 4 plus 1 by 6. So this is the result. But simple deduction. We have this result. So in this result, just put a equal to 1, b equals to 4 by 3, then you can get the required result. Okay. So this is second questions. By using either Rolle's theorem or mean value theorem, you can solve questions. Okay. So here, just for your practice, just I will give some questions for your practice and do it from yourself in your copy. Okay. So write and solve all the questions. So first question is, one, prove that log 1 plus x equals to x by 1 plus theta x. X by 1 plus theta x, where theta lies between 0 to 1, and hence deduce that hence deduce that x by 1 plus x is less than log 1 plus x is less than x. X greater than a. Here x greater than a. Just this is a question. Just you have to complete it. Okay, first question. Prove that log 1 plus x equals to xy 1 plus theta x. Okay. So just similar to the previous question, here for solving these questions, you have to let the function fx equals to. So you can take fx equal to log 1 plus x and then use mean value theorem, second form of mean value theorem. You know the second form of mean value theorem is what? Just we know f a plus x, the second form. For solving these questions, you can solve it. Very simple. Second form of mean value theorem, just use. Here let fx equals to what? Log 1 plus x. Fx equals to log 1 plus x, like this. For this you can prove it by using mean value theorem. Second form. Second form like this, a plus h might equals to fa plus h f dash a plus theta h, where theta lies between 0 to 1. Okay, this is second form. Second form, Lagrange mean value theorem. Second form. By using this you can prove it. Okay, just take here what? Interval 0 to x interval. Just take 0 to x interval. What? A equals to 0 and a plus h equals to x. That is h equals to x. Just put here. So h equals to a equal to 0. So what do we get? If this, then here what? A fx equals to here f0. Here h means what? X. F dash. Just differentiate it. What? 1 upon 1 plus x. Just 1 upon 1 plus this theta x. Theta x. This. Okay. So what? Fx means log 1 plus x. Log 1 plus x equals to x upon 1 plus theta x. 1 plus theta x. That's proved. And for getting second result, just you can use like this. Theta lies between 0 to 1. Just find the value. Multiply 0 less than theta x less than x. Just multiply 1. 1 less than 1 plus theta x less than 1 plus x. Just revert it. So 1 greater than 1 upon 1 plus theta x greater than 1 upon 1 plus x. Just like this. So 1 upon 1 plus theta x equal to this. Just multiply x, x. Just like this. So x upon 1 plus x is less than this. This means what? This is less than x. Proved. Just as previous questions. By using second form of Lagrange mean value theorem. Okay. So this is first question. You have to do. Okay. And take second question. Second question, verify Rolle's theorem. Verify Rolle's theorem for the function fx equals to x plus 2 x plus 2 to the power minus x by 2 in the interval minus 2 0. Very simple questions. Just you can see that this e to the power this is exponential function, and this is also polynomial, and multiplying you get polynomial function. It is continuous, and also the polynomial function may be differentiable, that is differentiable. And Rolle theorem for minus 2, just you can see just 0, or you can see here. Okay, so thus see that what f minus 2 equals to 0, f 0 equals to 0. Rolle's theorem condition satisfied. Just find derivative, which you can find derivative and equals to 0, value x equal to this, and one of the value must contain in minus 2 0. Then we can say that Rolle's theorem is verified. Okay. Similarly, for Rolle's theorem, verification of Rolle's theorem, just this is first function. For the function first function, this second function. First is this. For second function is also, there is second function also. Verify for this. What? Rolle's theorem. Fx equals to 3x to the power 4 minus 4x square plus 5 in minus 1 1. 3x to the power 4 minus 4x square plus 5. Verify Rolle's theorem. 3x to the power 4 minus 4x square plus 5 in minus 1 1 interval. Okay, so just this is given function and this is interval. Verify Rolle's theorem. Okay, and another question is also there. 3 parts are there in this question. Okay, so here see, x minus a to the power m, x minus b to the power n. Fx equals to x minus a to the power m, x minus b to the power m, where mn are positive integer in AB. In this question, interval is AB. Function is this, x to the power minus a to the power m, x minus b to the power n, where mn are positive integer. In interval AB, just we have to verify Rolle's theorem. So by simple process, you can see that these two are polynomial function. Just polynomial function, so it is continuous for all values of x, and also fx is will differentiable, because polynomial function can be differentiated. So differentiable, and f equals to 0 and f b equals to 0. we can see. So Rolle's theorem for verification, just differentiate it and find the value of x. Another value of x must be lie in open interval AB. Then theorem will be verified. So just do these three questions for verification of Rolle's theorem. Now here one theorem is also there, Cauchy's mean value theorem. The Lagrange mean value theorem is main. Lagrange mean value theorem is main part. Main theorem, okay. And its particular form is Rolle's theorem. So here just general form, generalization of this theorem. Very generalization is what? Lagrange mean value theorem. Generalization mean value theorem is Taylor theorem. But here Cauchy's mean value theorem is also a statement. That is what? If Cauchy's mean value theorem. Cauchy's just write if Cauchy's mean value theorem. This is general form. A statement. If first fx and gx are continuous. Here are two functions. Up to now we have seen that there is single function fx. Here fx and gx are continuous in closed interval AB. And second, fx and gx are differentiable in open interval AB. Okay, and also with what? Third condition. This, and third condition is also, and also gx is not equals to 0 for any value of x in AB. G dash x equals to not 0. G dash x is equal to not 0. Yes. This is the three condition. For Cauchy's mean value theorem, general mean value theorem actually, because fx and gx are continuous in this interval, these are differentiable in open interval, and also g dash x is not equals to 0. Then there exists a point C in open interval AB such that FB minus FA upon GB minus GA equals to F dash C upon G dash C. Okay, so this is the statement of Cauchy's mean value theorem. Just yes, very simple. It can be seen that this theorem is generalization of mean value theorem, because from this theorem we can get Lagrange mean value theorem, Cauchy's mean value theorem. Lagrange mean value theorem can be obtained from this. If we take gx as a identity function, gx. If we take this, then we get Lagrange mean value theorem. Okay, because its derivative g dash x 1, here will be 1, f dash c. G x equal to x means gb minus ga means b minus a. So b minus a. So just like Lagrange mean value theorem. So Lagrange mean value theorem is particular form of this Cauchy mean value theorem. For Cauchy mean value theorem, there are two functions. This is the statement. Just remember it. It can be also proved. To prove it, we let, just like in the proof of Lagrange mean value theorem, what fx equals to what? By taking, we can suppose, just like what was there, fx plus a into x, in place of x just put gx. By taking this, now we can show that this function satisfies Rolle's theorem, and by Rolle's theorem there is a point f dash c equals to capital F dash c equals to 0, and just we can get two values. This such that also here by using this we can prove it very simply. Just we can see that f a equals to fb, just this like this, such that f a equals to fb, and we can do just as the previous Lagrange mean value theorem proved. From here, solving this, you can get a value, and f dash c, it will satisfy Rolle's theorem condition, so f dash c equals to 0. From here also you can get a, and but equal this to a, you can get this result. Okay, so there is a questions related to this theorem. Also you have to do these questions in your copy. Okay, so write for this Cauchy's mean value theorem. Verify Cauchy's mean value theorem for function verify Cauchy's mean value theorem for the functions Cauchy's mean value, verify Cauchy's mean value theorem for the functions e to the power x, e to the power minus x in the interval a b, e to the power x and e to the power minus x in the interval a b. Okay, Cauchy's mean value theorem. Just we can discuss about this is take fx equals to e to the power x, gx equals to e to the power minus x, both are continuous differentiable. Okay, and also we see that differentiation of this is not equals to 0 at any point in AB. So we can use we can see that the condition of first main value theorem are satisfied. For verification, just we have to find the value of C lies between A and B. For finding that C, how? Just use FB minus FA upon ZB minus ZA equals to F dash C upon Z dash C. Find all the values and put here and just solve. Then you can get the value of C in terms of A and B, in terms of A and B, and that will belongs to A interval B. If C belongs to this, then the theorem will be verified for these two functions. Okay, so do it also in your copy. Now take another question. For verify Lagrange's mean value theorem. Verify Lagrange's mean value theorem for fx equal to log x for the function fx equals to log x to the base e, log x to the base e in the interval 1 e. Okay, and fifth question. If fx plus h equal to this, if x plus h equals to fx plus h x plus theta h, fx plus h f dash x plus theta h, then find theta for the function fx is equals to ax square plus bx plus c in the interval ax square plus bx plus c in the interval 0 1. Okay, so this is given. What? This is another form of Lagrange mean value theorem. If this, that means Lagrange mean value theorem is given, just we have to find the value of theta for the interval 0 1. So just find all the values fx plus h, fx, and also its derivative. Just put all the values here. You can just, because you can put here the value. Okay. So this is simple process. Okay, here just we take interval how x plus h. This is x, this is x plus h. That is x equals to 0. That is, this is x and this is x plus h. That is x equals to 0 and x plus h equals to 1. That is h. So h equals to 1. X equals to 1. So you can get the value h equals to 1. Now, just find x equals to 0, h equals to 1. Okay. So here, fx plus h can be find 0, fh, f1, f1 can be find, fx can be find f0, h equal to 1, here x0, theta, h equals to 1. Just put here and just find its derivative and use here, then you can get the value of theta. Okay, now it can be solved. Here this is a and this is b. Just use Lagrange mean value theorem. fb minus fa upon b minus a equals to f dash c. Just find the value of c. Just you have to verify. C belongs to 1 and e. 1 and e means 2.71 something. Okay. So these are the questions for your practice. So do it in your homework copy. Okay. And practice some questions from different books related to Lagrange mean value theorem, Rolle's theorem. Okay.